Okay, I've been harping on you for a few weeks now about the importance of the mean value theorem. So here's our first lesson on the actual mean value theorem itself. So we're going to sketch a function f that is continuous on a closed interval and differentiable, thus smooth on the open interval. And we're going to have that f of a doesn't equal f of b, f of a and b are not zero, etc., etc. So essentially it just means like draw a very rough sketch that looks, I don't know, something like that. Okay? So now choose 2 points, A and B, and we'll give them their f of A and f of B outputs, right? So let's pretend that A were right here, so its output is f of A, and that B might be right here, so that its output would be f of B. So we've now labeled a diagram with both A and B and f of A and f of B. Then we are supposed to draw a secant line between f of A and f of B. So let's do that there and there. And so if I were to sketch in this secant line, there we go. Notice that the secant line has a particular slope, namely rise over run, right? The slope would be f of b minus f of a over b minus a. And then there is a point C where the slope of the tangent is the same as the slope of that secant. In our diagram, it looks like that point might be right about there, right? Notice if I were to draw in a dotted tangent line at that point, how it looks like it's pretty parallel. It's almost the exact same slope as the secant line in red. So that point would be located approximately right there. So from that point C, we have drawn in a tangent, and that tangent looks to be about parallel to the red. But since it's a tangent line at C, what is the slope of that tangent line? That would be f prime of C. And this is what leads us into what's called the mean value theorem, or as I like to refer to it, the MVT of calculus, the mean value theorem, the most valuable theorem. And what the mean value theorem says is that if f is continuous on a closed interval and f is smooth, is differentiable on the corresponding open interval, if those two conditions hold, then there is a C located between A and B where the slope of the tangent line at C, f prime of C, can be made equal to the slope of the secant line between the endpoints on the interval, f of B minus f of A over B minus A. So on the AP exam, the construction will always look approximately the same. Your answer for an argument about the mean value theorem will be yes, right? They'll say, does there exist a C that makes something explain why? And you'll say, yes, since f is continuous on some interval and differentiable on the open interval, then by the mean value theorem, there has to exist a C in the open interval where f prime of C equals whatever that template is saying on the interval. If it doesn't work, if the MVT doesn't apply, then it'll either be f is not continuous or it'll be f is not differentiable. And so your goal becomes figuring out why it's not continuous or why it's not differentiable on whatever that interval is. So let's go to an example. Determine whether there is a number C in the interval from 0 to 3 such that f prime of C equals f of B minus f of A over B minus A, where f of x equals radical x plus 1. So the answer to this is, well, notice that this function right here on the interval from 0 to 3, this is a continuous function, and it is differentiable. In fact, it's continuous and differentiable on -1 to infinity, right? For all numbers greater than or equal to -1, it is continuous, and for all numbers bigger than -1, it is differentiable. So we would say, yes, on 0 to 3, f is continuous, and on 0 to 3, f is differentiable. Thus, by the mean value theorem, there is a special number c in the interval. In this case, we want it on 0 to 3, in the interval from 0 to 3, where f prime of c can be found to be equal to f of b minus f of a all over b minus a. Notice f of 3 is radical 3 plus 1, radical 4, which is 2, minus f of 0, so that'd be radical of 1, which is 1, over 3 minus 0, so 2 minus 1 over 3 is 1/3. The second part of this problem actually asks us to find where that happens, right? Find all values of c. So notice that we can take the derivative, since f of x equals radical of x plus 1, in other words, x plus 1 to the 1/2, that means that f prime of x is equal to 1 over 2 x plus 1 to the negative 1/2 multiplied by 1 by the chain rule, so not really important, or not anything extra, I should say. It's important, but not extra. And we need to set that equal to the secant line slope that we found. So we need to set this equal to 1/3. This, of course, would happen if 1 over 2 radical of x plus 1 were equal to 1/3, which happens when 2 radical x plus 1 is equal to 3, which happens when radical x plus 1 is equal to 3/2, x plus 1 equals 9/4, and x equals 5/4, or about 1.25. And notice 1.25, or 5/4, is indeed in the interval from 0 to 3. So this would be a complete way of handling this question, which is saying show that such a number exists. Use the template to justify that it exists, and then actually find it. Okay, the other part of this lesson is about the intermediate value theorem, which we have done in class on previous places, so I'm just going to bring your attention to our template for constructing an argument. This one only needs continuity. So continuity, or justification on an exam, would be since the function is continuous on some interval, and w is a number in between f of one endpoint and f of the other endpoint, that means that there has to exist some c in the closed interval where f of c equals that particular w. We've already done arguments like this in class, and now we can see how mean value theorem and intermediate value theorem are similar templates but imply different things. And then the next page is going to be your problem set. So we'll do those in class on the day that we cover these.